Welcome to the deep dive. Have you ever stopped to wonder how the most advanced AI models actually think?
It's a great question, isn't it? I mean, we see these amazing outputs, but what's really happening behind the scenes?
Exactly. We're not just talking about spitting out answers instantly, but, genuinely going through some kind of reasoning process step by step before they arrive at a conclusion.
Right, like mimicking how we might puzzle something out.
Yeah. And it's especially relevant now with this new generation of models that claim to do just that.
You're talking about the LRMs, the large reasoning model.
Precisely. Today, we're diving headfirst into the exciting and maybe sometimes perplexing world of these LRMs. You might have heard names like OpenAI's O3, Claude Sonnet Thinking, DeepSeek R1.
These are the ones making waves, claiming enhanced reasoning.
They are. And what makes them so compelling is their core promise. They generate these detailed thinking processes, often called chain of thought or coity, before giving their final answers.
So instead of just the answer, you get the working out, supposedly.
Exactly. Imagine asking, I don't know, what's 25 times 12? A standard model might just pop out 300.
Instantly, yeah.
But a chain of thought model, it might internally break it down. It might think, okay, 25 times 10 is 250. Then 25 times 2 is 50. Adding 250 and 50 gives me 300.
That step-by-step internal monologue, that's the SUOT.
That's it. And this approach, the SUOT, has led to some really impressive improvements on complex benchmarks. It makes them seem incredibly intelligent, capable of, well, truly reasoned thought.
Which is the big promise, right? Moving beyond just pattern matching.
But here's the kicker, and this is really the fundamental problem that kicks off our deep dive today. Despite this, outwardly impressive performance, our fundamental understanding of these LRMs, what they're truly capable of, how their abilities scale when problems get harder, and crucially, where their limitations really lie, it remains surprisingly unclear.
So there's a gap between what they do and what we understand about how they do it.
Exactly. Current evaluations, they mostly focus on those established math and coding benchmarks, just looking at final answer accuracy.
Like Math 500, things like that.
Right. And the big issue there, it's something called data contamination.
The idea that they might have already seen the answers or very similar problems in their training data.
Precisely. So are they genuinely reasoning through a new problem? Or are they just sort of pattern matching or recalling solutions they encountered during their massive training?
It's the difference between solving and just recognizing. A huge difference.
And maybe even more importantly, these traditional tests don't give us any insight into how the models think. They don't expose the structure, the quality of those intermediate steps, those reasoning traces.
You just get the final number, the final piece of code, pass or fail. No insight into the process.
Which means we can't really tell if the reasoning was sound or just lucky or flawed but happened to land on the right answer.
Right. That lack of visibility is a major blind spot.
So, our mission today is to unpack a groundbreaking research paper from Apple. It's titled, The Illusion of Thinking: Understanding the Strengths and Limitations of Reasoning Models via the Lens of Problem Complexity.
The Illusion of Thinking. That's quite a title. Suggests they found some interesting discrepancies.
It really does. And this paper offers a truly systematic, really rigorous investigation into these knowledge gaps. And they use a novel approach, a very insightful one, that moves beyond those standard benchmarks.
Okay, I'm intrigued. What's the novel approach?
We'll get right into that. And
Right.
what you're going to learn today might just surprise you. We'll explore this new way to evaluate them, uncover some unexpected, frankly counterintuitive collapses in their performance.
The lapses. Wow.
Yeah, we'll see some puzzling behaviors in their thinking effort and delve into some truly fascinating discoveries about their internal reasoning processes.
So not just the good, but the bad and the ugly, too.
Exactly. It's not just about what these powerful AI models can do, but really digging into what they can't do, and maybe starting to understand why that's so critical for the future of AI. It's about pulling back the curtain on that thinking process itself.
Sounds like a much-needed reality check, perhaps.
Could be. So with that problem statement in mind, let's unpack this research paper and see what it truly reveals about the thinking happening inside these powerful AIs.
All right, let's do it. It's quite a significant journey, isn't it? From where we started with large language models, the LLMs.
Absolutely. Feels like just yesterday we were amazed by basic text generation.
Right. If you think back, LLMs really impressed us with their ability to understand, generate human-like text, summarize things, translate.
Just handle language with incredible fluency.
Yeah, they were, fundamentally about mastering the nuances of human communication. But then came this evolution, this shift, where researchers started specializing these LLMs into what we now call large reasoning models, or LRMs.
Right. It's like LLMs learn to talk, and now LRMs are attempting to learn to think before they talk. Or at least that's the goal.
That's the ambition, yeah. They are specifically designed or tweaked for these complex reasoning tasks.
Yeah.
And their defining characteristic, as you mentioned, is that thinking mechanism.
The chain of thought, the COT.
Exactly. We're talking about technologies that generate these extended COT sequences, sometimes even engaging in what's called self-reflection.
Where they supposedly check their own work, try to refine things.
That's the idea. Trying to catch errors, refine answers. We've seen examples like DeepSeek R1, Claude Sonnet thinking, Gemini thinking, all pushing this frontier of computational reasoning.
It sounds very sophisticated.
It does. And some researchers have even, gone so far as to call this a paradigm shift.
A paradigm shift? That's a strong claim. Why?
Well, for an audience like ours, people who follow AI closely, it's seen that way because it suggests a path beyond just, sophisticated pattern matching and statistical association.
Moving beyond correlation to something closer to causation or logic?
Potentially. It hints at the possibility of genuine, maybe emergent intelligence systems that can truly understand causality, follow complex logical paths, solve problems that need more than just recalling patterns from enormous data sets.
So the promise is that LRMs are significant steps towards more general AI capabilities.
That's the hope. Moving beyond language processing to something that truly approximates human-like reasoning. However, as this Apple paper highlights, the fundamental benefits, and maybe more importantly, the limitations of these LRMs, they aren't as clear-cut as they might seem on the surface.
Right. Are they genuinely capable of generalizable reasoning? Or are they, as the paper puts it, just leveraging different forms of pattern matching, but in a more complex, multi-step way?
That's the million-dollar question, isn't it? Is it real reasoning or just a more elaborate illusion of it?
And that's precisely where those traditional evaluation methods really fall short. You mentioned Math 500, AIM 24, M25.
Standard benchmarks for math and coding reasoning.
Yeah. And the core problem, as the paper details, is that data contamination issue.
Which we touched on. The fear they've seen the answers before.
Exactly. These benchmarks have been out there, publicly available for a while. These models train on just vast swaths of internet data. It's almost certain they've encountered these specific problems or problems incredibly similar to them during training.
So when they solve one,
the crucial question becomes, are they genuinely reasoning it out from first principles using logic? Or are they just recalling a memorized solution pattern, effectively regurgitating something they've already seen?
It makes it really hard to tell if you're testing reasoning or just, memory retrieval on a massive scale.
It absolutely does. And beyond that, these traditional benchmarks, they only give you that binary outcome, right or wrong, pass or fail.
Yeah, no nuance.
They provide zero visibility into the structure and quality of intermediate reasoning traces. You don't see how the model got there. Was its internal thinking logical? Was it a lucky guess after a flawed process?
We just don't know. They tell us nothing about the efficiency, the robustness, the quality of the internal problem-solving process.
Take something like Pass-It-K performance. That's how often the model gets a correct answer within its top K tries, right?
Right, like Pass-It-1 is getting it right on the first attempt. Pass-It-5 is within the top 5 attempts.
So if Pass-It-1 is low, it means it rarely gets it right first time. But even if Pass-It-K is high, you still don't know if the reasoning behind the correct answers it eventually found was any good.
Exactly. You need a much more controlled, more transparent environment to really understand the reasoning behavior.
So the researchers in this Apple paper, they propose an innovative and I think quite elegant solution to this very problem.
Okay, here we go. The novel approach.
Instead of relying on those potentially contaminated, definitely opaque math benchmarks, they adopt controllable puzzle environments.
Puzzles.
Like logic puzzles.
Exactly. Things like Tower of Hanoi, river crossing problems, checker jumping. And this is really where it gets exceptionally interesting. What makes them controllable?
You can adjust the difficulty somehow.
Precisely. It's the ability to precisely manipulate what they call compositional complexity. Compositional complexity. Break that down for us.
Think of it like building with Legos. Low compositional complexity might be just connecting two simple blocks. Requires one step, very straightforward.
Okay.
Medium complexity might be building a small house. You have several interdependent parts. Walls support the roof. Windows fit in walls. Takes multiple steps, requires some planning.
Got it.
High compositional complexity. That's like building a sprawling, intricate castle. Complex towers, hidden passages, maybe multiple wings, hundreds of pieces, long sequences of steps where one depends heavily on the previous one.
Okay, so you're increasing the number of steps, the dependencies, the length of the required solution.
Exactly. The core rules of Legos, how pieces connect, stay the same. But the number of steps, the depth of dependencies, the overall solution length, they increase dramatically. That's what they mean by controlling compositional complexity in these puzzles. They can systematically make the same underlying logic problem much, much harder just by increasing n, the number of elements.
Yes, that's a brilliant methodological pivot, it really is. Because these puzzles offer several key advantages that traditional benchmarks just can't match.
Like what?
Well, first, as you highlighted, you get that fine-grained control over complexity. You can systematically dial up or dial down the difficulty, often just by changing one parameter, like the number of disks in Tower of Hanoi, without changing the fundamental logical rules of the puzzle itself.
So you can really probe how performance scales with difficulty in a very precise way.
Exactly. Second, these puzzles specifically require algorithmic reasoning. The models are given only the explicit rules of the game, how the pieces move, what the goal is. They can't just rely on some fuzzy learned pattern from pre-existing web data about, say, calculus problems. They must follow a clear, logical sequence of steps derived only from those explicit rules provided in the prompt.
Which forces them to actually try and compute the solution based on the rules, not just recognize a pattern.
Right. And this setup also inherently avoids data contamination. The researchers can generate fresh, unique puzzle instances on demand, ensuring the model hasn't seen that exact configuration before.
That's huge. Eliminates that whole memorization question.
It really helps. And crucially, these puzzle environments support rigorous simulator-based evaluation. Meaning they can do much more than just check the final answer state. They have a simulator that knows the puzzle rules perfectly, so they can perform precise solution checks, step-by-step, and detailed failure analyses by examining the internal reasoning traces the sequence of moves or thoughts the model generated.
So you're not just seeing if the model got the final configuration right, but also how it got there, and crucially, where it went wrong if it failed.
Exactly, step by agonizing step sometimes. This offers an unprecedented window into the actual problem-solving approach, the thinking process of these AIs. You see the quality of the journey, not just the destination.
What's fascinating here, then, is how the researchers moved beyond just looking at the surface, beyond the standard, often black box benchmarks.
Absolutely. If you connect this to the bigger picture, it's really about shifting from just measuring what the model knows or appears to know to understanding how it knows it. Or perhaps more fundamentally, if it even truly knows or understands at all in the way we mean it.
It's moving towards a more mechanistic, more transparent understanding of these incredibly complex systems.
Which is absolutely vital if we're going to develop and deploy them responsibly and effectively. We need to know their real strengths and weaknesses, not just the ones suggested by potentially flawed benchmarks.
Okay, so armed with this innovative evaluation method using these controllable puzzles, the researchers set up some pretty extensive experiments.
They test.
They focused on some cutting-edge frontier LRMs. Specifically, they looked at matched pairs comparing models with and without that explicit thinking mechanism enabled.
So direct comparison, like A versus B.
Exactly. They studied Claude 3.7 Sonnet, both its thinking and non-thinking variants, and they compared DeepSeek R1, which is a reasoning model, against DeepSeek V3, its non-thinking counterpart.
Okay, state-of-the-art models, and they made sure the comparison was fair.
Seems so. They gave these models an ample token budget up to 64,000 tokens. That's a massive amount of thinking space, way more than needed for even the complex puzzles.
So they wouldn't run out of room to think, essentially.
Right. And they ran 25 samples, 25 attempts per model, per complexity level, to ensure the findings were robust and not just flukes.
Good methodology. Multiple runs are key.
This meticulous setup allowed for a direct, controlled comparison, really zeroing in on the specific impact of that thinking mechanism. Does it help? When does it help? How much does it help?
Okay, so what did they find? Did they look at the old benchmarks first?
They did. And their initial findings on the traditional math benchmarks, while seemingly straightforward at first glance, quickly revealed those interpretive challenges we discussed.
The contamination issue rearing its head.
Pretty much. For instance, on some benchmarks like Match 500, the paper confirmed that thinking models, given the same compute resources, had, well, comparable pass-at-K performance to their non-thinking counterparts.
Comparable. Not significantly better.
not significantly better on that one. Which in itself hints that simply adding a thinking step doesn't automatically grant a huge advantage on all tasks, especially maybe those where a non-thinking model might rely on highly optimized pattern recognition honed over massive data.
Interesting. So thinking isn't a universal booster.
But then it gets trickier, and this is where the puzzle really deepens. On AIM-24, another math benchmark, the performance gap between thinking and non-thinking models widened. LRMs showed an edge there.
Okay, that sounds more like what you'd expect. Harder problems benefit from reasoning.
Right. And the gap widened further on AIM-25. So you might initially think, aha, as problem complexity increases, thinking models truly shine.
Makes intuitive sense.
However, and this is a critical observation the paper points out, there's a fascinating detail about human performance. Humans actually performed better on AIM-25 than on AIM-24.
Wait, humans found AIM-25 easier, but the models found it harder, or at least the thinking model showed a bigger advantage there.
Exactly, which suggests AIM-25 might actually be less complex, or at least differently complex, for humans.
That throws a wrench in things.
Yeah.
If models struggle more on a task humans find easier, what does that say about the task or the models?
It strongly suggests a classic case of data contamination during training, doesn't it? It points back to models perhaps learning specific patterns unique to certain test sets, rather than developing a truly generalized reasoning capability that aligns with human understanding of complexity.
So it really raises that question again. Are models just getting better at acing specific tests they might have effectively studied for? Or are they genuinely improving their underlying generalizable reasoning skills?
Precisely. And it underscores exactly why a controlled environment, like these puzzle environments the researchers used, is so absolutely critical for uncovering true capabilities away from the shadow of potential data contamination.
Okay, so let's get to the puzzles. What did they reveal?
This is where the revelation of the three distinct regimes of complexity comes in. Discovered through these controlled puzzles, this is really a core, groundbreaking finding of the paper. It shows how nuanced and, frankly, counterintuitive LRM performance actually is. It challenges a lot of our assumptions.
3 regimes based on complexity.
Yes. Let's start with regime 1, low complexity. Puzzles that require only a few straightforward steps to solve.
The easy stuff.
Right. And what's truly surprising here is that for these simpler, low compositional problems, the standard LLMs, the non-thinking ones, were actually more efficient and consistently accurate than their LRM counterparts.
Wait, the non-thinking models beat the thinking models on easy problems.
That's what the data showed. The models specifically designed to think actually got tripped up by the easy stuff, or at least performed worse, both in terms of accuracy and efficiency.
That seems completely backward. How could that happen?
Well, the paper suggests a couple of possibilities. Maybe the overhead, the inherent nature of the thinking process itself, actually becomes a detriment at lower complexities. It adds unnecessary steps or potential points of failure.
Like bringing a sledgehammer to crack a nut. It's overkill and might just make a mess.
Kind of. Or maybe the standard LLMs are simply more optimized for that kind of quick, straightforward pattern recognition that perfectly solves these easy problems without needing an elaborate thought process. Their direct approach is just better suited.
So for simple tasks, the thinking mechanism might be more hindrance than help. That's fascinating. What's regime 2?
Regime 2 is medium complexity. Here, as problem complexity moderately increases, needing more steps, more interdependencies, but still within a, let's say, manageable scope, the thinking models, the LRMs, do gain a significant and clear advantage.
Ah, okay. This is where they start to shine.
Exactly. This is the sweet spot. This is where their chain of thought mechanisms truly demonstrate their value. They help the models navigate the more intricate logical steps, keep track of state, and derive correct solutions where the non-thinking models start to falter or fail completely.
So this regime validates the core premise of LRMs. That generating intermediate thoughts helps for moderately challenging problems.
It absolutely does. It shows that for a certain range of complexity, generating those intermediate steps truly helps guide the model to the correct solution. The CAFOOD is beneficial when the problem isn't trivial, but also isn't overwhelmingly complex. This is where they look like they're genuinely reasoning effectively.
Okay, makes sense. There's a zone where the thinking pays off.
Yeah.
You said 3 regimes. What happens next?
Right. Then we hit regime 3, high complexity. And this is perhaps the most concerning and certainly the most revealing finding in the entire paper.
Oh.
When problems reach a high compositional depth puzzles with extremely long solution paths demanding many, many sequential interdependent steps, something dramatic happens. Both model types, the thinking LRMs and the non-thinking LLMs, experience a complete performance collapse down to near zero accuracy.
A complete collapse. For both, even the ones designed to think.
Even them. It's like hitting an impenetrable brick wall. Accuracy just plummets, regardless of how much thinking the LRM is designed to do.
Wow. So the thinking helps them get a bit further, maybe handle slightly harder problems than the non-thinkers.
Exactly. The paper emphasizes that thinking models only delay this collapse. They might push the wall back a few steps, handle N10 instead of N8, for example. But they don't prevent the collapse. They don't solve the underlying issue.
So there's a fundamental limit they just can't seem to overcome, thinking or not.
That's what the researchers conclude. They call it a fundamental inference time-scaling limitation. Essentially, there seems to be a hard limit to how much complex, sequential, step-by-step reasoning these models can reliably perform during inference when they're actually trying to solve the problem.
It's not just about knowledge. It's about the computational process of reasoning itself breaking down.
Precisely. Throwing more thinking at them via C only pushes that limit slightly. It doesn't fundamentally break through it.
This three regimes finding is absolutely critical then, because it directly challenges that simple narrative that more thinking is always better, or that these models are on some smooth, inevitable path to general intelligence.
Yeah, it paints a much more nuanced picture, a landscape where simplicity can surprisingly be a hurdle for complex models. Moderate complexity is where they shine, and extreme complexity remains, for now at least, an insurmountable barrier. It really exposes the potential illusion of truly scalable reasoning.
Okay, that scaling limitation is a huge point. How does that relate to the effort they put in? Do they try harder on the hard problems?
Well, that's where things get truly puzzling and, again, counterintuitive. The paper highlights this counterintuitive decline in thinking tokens. Remember, thinking tokens are a measure of the amount of internal thought, the length of the Shojaee that the model generates.
Right. More tokens should mean more thinking effort.
You'd think. But what happens is that near the collapse point, as problems become overwhelmingly difficult, the LRMs actually begin to reduce their reasoning effort. The number of thinking tokens they generate starts to go down, even as complexity is still going up.
They generate less thought when the problem gets harder. But why?
Okay.
They have the budget, right? You said 64K tokens.
Exactly. They are operating well below generation length limits and have ample inference budget. They could generate much longer chains of thought. They have the computational space and the tokens available, but they just don't.
It's like they give up on generating long thought chains when the going gets really tough.
That's what it looks like. It implies it's not simply a matter of resource constraints, like running out of memory or tokens. Instead, this behavior strongly suggests a fundamental scaling limitation in their reasoning capabilities relative to the problem complexity.
So it's as if when the problem hits a certain threshold of difficulty, the model's internal process itself becomes inherently inefficient or maybe unstable, or it just stops trying to extend the thought process effectively.
That seems to be the implication. It's a systemic failure to scale their own internal processes effectively when faced with truly hard long-chain reasoning problems. This is a critical insight into their core design, maybe, and how they interact with complexity.
That is deeply counterintuitive. Less effort for harder problems.
Isn't it? And this is where the paper's use of those controlled puzzle environments really shines again, because it allowed the researchers to actually dive into the thoughts of these models.
To look at the content of those thinking tokens, not just the quantity.
Precisely. They conducted a fine-grained analysis of the internal reasoning traces, going beyond just the final answer or the token count. It's like peeking inside the mind of the AI, seeing its step-by-step internal monologue, which, as you said, was illustrated nicely in their Figure 1, showing a model's attempt at solving a puzzle, thought process, and all.
And what did they find when they looked inside? Were the thoughts logical?
Efficient? Well, what they found were truly fascinating and, again, complexity-dependent thought patterns. It wasn't uniform at all. The nature of their thinking changed dramatically based on the problem's difficulty, aligning with those three regimes.
Okay, so what did thinking look like in Regime 1? The simple problems where they performed worse.
This is where they observed what they termed overthinking.
Overthinking.
Yeah. Take the classic Tower of Hanoi puzzle with just any two disks. It's a trivial problem, just a few moves. The models would often find the correct solution very early in their thinking process, maybe within the first few thought tokens.
Okay, so they solve it quickly.
But then they don't stop.
They just keep going, like someone meticulously double-checking their grocery list for a single item, Even though they only have milk written on it and they've already confirmed it's in the cart, they just can't stop thinking about it.
That's a perfect analogy. The paper says they would then continue exploring incorrect alternatives or redundantly re-verifying the already correct solution they found earlier.
So, wasting time and compute cycles.
Exactly, leading to significant waste of compute and demonstrating significant inefficiencies. The paper even gives a specific anecdote. Claude 3.7 Sonnet, doing this for Tower of Hanoi N2, repeatedly confirming the same correct solution while spending a considerable number of tokens that could have been used much more efficiently.
So the interesting inefficiency where more thought actually becomes detrimental or at best just unnecessary overhead. It looks like deep thought, but it's masking inefficiency, another layer to the illusion.
Right. But then contrast that with regime 2, moderate complexity. Here, the pattern shifts entirely.
No more overthinking.
No. Instead, the models engage in extensive exploration. The correct solutions typically emerge only after a thorough exploration of various incorrect paths and dead ends.
Ah, so here the long chain of thought is actually productive. It's necessary exploration.
Precisely. This clearly shows the value of code in these scenarios. The process of trying, failing, maybe backtracking, exploring different routes, that's what ultimately leads them to the right answer. It's where the code mechanism truly earns its keep, enabling them to solve problems the non-thinkers can't.
Okay, so productive thinking in the middle ground.
Yeah.
What about regime 3, the high complexity collapse mode? What do the thoughts look like there?
Well, the behavior here is quite stark and frankly concerning. First off, models completely fail to find correct solutions. Accuracy is near zero.
Yeah, collapse.
But what are they thinking while they fail? Instead of productive exploration, they seem to fixate on early incorrect attempts.
Fixate, like they get stuck on a wrong idea.
Exactly. They make a mistake early on, and then they just waste the remaining, often substantial inference token budget digging themselves deeper into that error. They generate long but ultimately incorrect chains of thought based on that initial mistake.
With no sign of self-correction, they don't realize they're on the wrong path and try something else.
Apparently not, or not effectively. This highlights a clear and profound limitation in their self-correction capabilities, especially when the problem gets really complex. They can't seem to course-correct or abandon a bad path once they're far enough down it. The thinking becomes a process of just reinforcing the initial error.
Wow. So the analysis of the internal traces provides this crucial window. It shows thinking isn't always efficient. Sometimes it's overthinking, and in hard cases, it can be just systematically failing to self-correct and wasting effort.
That seems to be the picture. It's perhaps the most profound part of the illusion it looks like thinking, because tokens are being generated, but it's a process leading nowhere useful or even actively detrimental.
Okay, so we've seen issues with scaling, effort, and the internal thought processes. Did the paper uncover other sort of puzzling behaviors about what these models still can't do?
Oh, absolutely. And these challenge some really fundamental assumptions we might hold about how they learn and operate. The most striking of these is what the paper calls the algorithm paradox, when explicit guidance fails.
Explicit guidance fails. What does that mean?
So the researchers conducted this really fascinating experiment. For puzzles like Tower of Hanoi and another called checker jumping, they didn't just give the rules. They explicitly gave the models, the solution algorithm, the exact step-by-step recipe for solving the puzzle right there in the prompt.
They gave them the cheat sheet, the exact instructions.
Pretty much. You'd think, okay, if all they have to do is follow a precise set of instructions, performance should skyrocket, right? Especially for complex versions of the puzzle.
Yeah, that seems logical. Execution should be easier than invention.
But the truly surprising finding was their performance did not improve. The accuracy collapse, that brick wall in regime 3, still occurred at roughly the same complexity points, regardless of whether they were given the algorithm or had to figure it out themselves.
Wait, let me get this straight. If you give them the recipe, step by step, they still can't bake the cake if the cake is complicated enough.
That's what the results indicate. It fundamentally challenges a core assumption about how we might use these models for complex, instruction-driven tasks. It feels deeply counterintuitive.
It really does.
Yeah.
Because logically, executing a known algorithm should require substantially less computation and, conceptual heavy lifting than devising that algorithm from scratch.
So what does that imply about the models?
Well, the paper argues it further highlights the limitations of reasoning models in verification and in following logical steps to solve a problem. It suggests deep issues with their fundamental symbolic manipulation capabilities.
Meaning their ability to correctly understand, process, and apply abstract rules and symbols in a consistent logical sequence, even when that sequence is handed to them, seems to have a hard limit.
Exactly. It's not just about finding the path. It seems they struggle even to follow a clearly laid out path if it gets too long or complex. And the researchers were careful here. They confirmed this wasn't just an artifact of Tower of Hanoi being maybe too common online. They tested it on checker jumping too, which has different characteristics and is less likely to be memorized, and found the same general limitation.
So it points to a more fundamental flaw in how these models process and integrate explicit step-by-step instructions when complexity scales up.
It certainly seems that way. The illusion here is perhaps that they appear to follow instructions perfectly on simpler tasks, but this experiment suggests that ability breaks down under sufficient complexity.
Okay, that's a big one. Failing to use the provided algorithm. What else?
It's not just about following algorithms. The paper also highlights significant, inconsistent reasoning across scales and puzzles.
Inconsistent how?
They observed what's called non-monotonic failure behavior.
Non-monotonic, meaning not smoothly increasing or decreasing.
Right. Sometimes models would fail earlier in the required solution sequence for higher complexity problems, like a larger n value, even though those problems require longer overall solutions.
Can you give an example?
Yeah, the Popper notes, for instance, that for Tower of Hanoi, a model might fail before completing 50 moves for N12 disks, but it might successfully generate more than 100 correct moves for N10 disks.
But N12 is harder and needs way more moves than N10, so it fails sooner on the harder problem, even in the early steps.
Yeah, exactly. This directly contradicts the expectation of consistent algorithmic planning, where you'd think if it can handle 100 steps for N10, it should at least handle the first, say, 70 steps for N12 before failing. Instead, the failure point seems almost erratic, not smoothly scaling with complexity.
That is weird. It suggests the planning isn't robust.
And it gets even more stark when you compare the varying error-free sequence lengths across different types of puzzles.
Well, so?
Models might be able to generate, say, up to 100 correct moves in Tower of Hanoi N10, which is quite impressive. But then, shockingly, only manage maybe 4 correct moves in River Crossing N3.
4 moves. For river crossing with only 3 pairs, that sounds much simpler than Tower of Hanoi N10.
Computationally it is. The paper points out that the state space, the number of possible configurations, for an 11-move solution in N3 river crossing is vastly smaller than the state space for a 10-23-move solution in N10 Tower of Hanoi, where models are succeeding for over 100 moves. Yet they fail almost immediately on the simpler river crossing.
So what's going on there? If it's not just raw computational complexity, what else could it be?
Well, the paper speculates, and this is crucial, that this inconsistency might suggest that models' perceived difficulty with a problem is more related to learned solution distributions from their training data.
Meaning how often they saw similar problems solved online during training.
Exactly. They might have had far less exposure to examples of complex river crossing solutions on the web compared to the very common Tower of Hanoi examples. So, their poor performance might stem from data sparsity for that specific problem type in their training set, rather than the problem's inherent computational complexity.
So it circles back to the training data again. It suggests they're still operating heavily on sophisticated pattern matching and statistical associations derived from what they've seen, rather than possessing a deep, abstract, generalizable understanding of algorithmic complexity itself.
That's a key interpretation. It reminds us that these models are complex artifacts, and their behavior isn't always directly correlated with our theoretical understanding of a problem's difficulty. Their performance is heavily influenced by the distribution and nature of the data they were trained on.
So their approach to complexity might correspond more to patterns I recognize from training than to abstract computational difficulty.
That seems plausible based on these findings. And that's why the paper focused on tracking behavior within each puzzle setting across complexities, rather than making direct comparisons between puzzles based solely on theoretical difficulty, because that comparison can be misleading if training data distributions are different.
It's another layer to the illusion. What looks like an inability to handle inherent difficulty might actually be, in part, a data sparsity or pattern recognition problem.
It's a really important nuance to grasp when evaluating these systems.
Okay, so we've covered a lot. The scaling issues, the weird effort reduction, the overthinking, the fixation on errors, the failure to use algorithms, the inconsistencies. What does this all mean then for the future of AI and how we interact with these incredibly powerful yet sometimes really puzzling thinking machines?
Well, this paper, The Illusion of Thinking, it really provides a comprehensive and I think quite sobering look at both the strengths and, perhaps more importantly, the significant limitations of these frontier large reasoning models.
Let's recap. On the strength side.
On the strength side, it's clear. LRMs do show an advantage at moderate complexity tasks. That regime, too, is real. And this advantage seems genuinely due to their thinking processes, their chain of thought.
So Cody isn't useless. It has a definite value proposition in that middle ground.
Absolutely. It offers a valuable bridge over the gap between simple pattern recognition and those really hard problems where everything currently breaks down. It does seem to enhance problem solving in that specific zone.
But the limitations, they seem pretty stark, and they really define that illusion the paper's title points to.
They do. First and foremost, despite all the hype, despite sophisticated mechanisms like self-reflection, these models still fail to develop truly generalizable reasoning that scales robustly beyond certain complexity thresholds.
We saw that clearly in the three regimes. Non-thinkers winning on easy stuff, thinkers winning in the middle, and then that universal stark collapse at high complexity for everyone.
Right. There's a fundamental wall they hit, no matter how much thinking architecture is bolted on.
And then there's that truly counterintuitive reduction in reasoning effort, fewer thinking tokens as problems approach that critical complexity wall.
Despite having the capacity, they seem to pull back, suggesting an inherent compute scaling limit or inefficiency in maintaining coherent, extensive thought when things get tough.
Add to that the demonstrated inefficiencies, that wasteful overthinking on simpler problems.
Where they find the answer, then keep churning.
And the opposite problem at high complexity, that early fixation on errors, where they waste their entire budget going down a wrong, unrecoverable path.
Highlighting profound limits in effective self-correction.
And maybe the most fundamental limitation, that puzzling inability to benefit from explicit algorithms.
Being given the recipe doesn't help them bake the complex cake. Suggests deep issues in following logical, prescribed steps robustly.
Coupled with their inconsistent reasoning patterns failing differently across scales, performing wildly differently on puzzles of arguably similar or even lower computational complexity.
All these findings together really challenge the prevailing narrative, don't they? The idea that current LRMs are steadily, smoothly progressing towards truly generalizable AI.
Yeah, the paper strongly suggests they might be encountering fundamental barriers to that kind of true scalable intelligence, rather than just needing more data or bigger models using the current architectures.
Now, it's important for us and for you, the listener, to acknowledge the study's own stated limitations. The researchers are commendably transparent about these in the paper.
Right. Good science acknowledges its boundaries. What did they mention?
They note they used a narrow slice of reasoning tasks, these logic puzzles. The findings might not perfectly generalize to all types of reasoning, especially real-world problems involving ambiguity, common sense, or retrieving external knowledge.
Okay, so puzzle solving might differ from, say, medical diagnosis reasoning.
Potentially. Also, relying on black box API access to closed models like Claude means they couldn't analyze internal states or architectural components in the deepest possible detail beyond the input-output tokens.
They couldn't crack open the box completely.
Right. And the deterministic puzzle simulators assume perfect step-by-step validation is possible, which might not hold true in less structured, messier domains.
So these limitations prevent a universal claim covering all AI reasoning.
Exactly. But they don't diminish the specific, crucial, and rigorously obtained insights gained from this controlled and highly revealing puzzle-based environment. They've shown a bright light on specific scaling and consistency issues.
Okay, so wrapping this up, what does this all mean for the future of AI, and maybe more importantly, for how we should think about and interact with these incredibly powerful, yet sometimes profoundly puzzling thinking machines?
Well, for you, the listener, these findings really raise some deep, maybe uncomfortable, open questions about the nature of AI intelligence itself.
Like what? What should we be asking?
Well, what does it truly mean for AI development if models don't reliably benefit from being given the precise solution algorithm? Is our current approach to training fundamentally missing something about how to integrate explicit instructions versus learned patterns?
That's a big one. How do we get them to reliably follow instructions?
And how can we train models to think more consistently and efficiently? How do we avoid both that wasteful overthinking on simple tasks and that premature collapse or error fixation on complex ones.
Can we teach them better resource allocation during thought? Better self-correction?
These are key research directions. How do we ensure models develop genuine algorithmic consistency, that predictable, reliable, step-by-step logic, rather than just relying so heavily on opaque patterns learned from potentially biased or incomplete training data?
What are the next fundamental steps needed to bridge that gap between sophisticated pattern matching, which they're amazing at, and true, generalizable, scalable reasoning?
These are the questions that will define and drive the next wave of AI research and development. This paper provides crucial data points for that journey.
That's all for this deep dive. We hope this exploration into Apple's Illusion of Thinking paper has given you a shortcut to being well-informed and perhaps sparked a few aha moments about the fascinating and, yes, sometimes illusory world of AI reasoning.
It's a complex picture, definitely not straightforward.
Definitely not. So consider this as a final thought. If even being given the exact instructions doesn't guarantee a solution from these advanced reasoning models when the problem gets hard enough, how much of what we currently call thinking in AI is truly robust understanding and problem solving, and how much is just a very, very sophisticated performance of looking like it? Something to ponder. We'll see you next time.